Hi folks, welcome to lecture 7. I'm going to share my screen. Take a second to load here. All right, so let's go over the next section. We're going to talk about statistical power and data transformations. This is a little bit shorter lecture, so you'll have a chance to work this out, but I just want to go over all the theories behind everything first. We're going to talk about type 1 and 2 error and different hypotheses. So we're testing our hypothesis and we're looking to find something that is within or outside of the 95%, okay? If it's within that 95%, you accept the null hypothesis, meaning that there is no difference, that your two samples are not different enough. If the outcome is part of that outside 5% extreme, then you're going to reject the null hypothesis, meaning that there is difference in the two samples and one of your alternative hypotheses could be correct. So we've talked about this a little bit already. Remember that probability is a percent. Statistic analysis, calculate the probability, which is the p-value, and that's what we're looking for. So the p-value is the probability that we will see a result in that outside area, okay? Whether or not, we always assume that the null hypothesis is true, meaning that there is no difference. However, the p-value will show us either we're correct and there is no difference if it's above 0.05, or if it's below 0.05, it lives out here in this outside range and in these very unlikely observations. And that means that there is a difference in our two samples. We interpret that we're comparing the observed p-value with the alpha level. All right, the alpha level is the cutoff, which is this over here on the left-hand side, this blue line right here. It's the cutoff for the rejection of the null hypothesis. It's the significance level, right? It's that outside of 95%. This is where type 1 error happens the most, when we accidentally reject the null hypothesis. So that's why we set our alpha levels at 0.05, or that extreme 5%. And with that outside 0.5%, the chances are only 1 in 20 that you would accidentally reject a true null hypothesis, saying that there actually is a real difference. P-values are considered statistically significant. And I know you've seen this chart before. So 0.05 is our cutoff. That's our traditional alpha cutoff. So if the observed p-value is less than 0.05, which is what our alpha level is, we reject the null hypothesis. Means that the outcome is so extreme that it's unlikely to have come from our population. Now, if the p-value is greater than our alpha level, which is 0.05, then we assume that the null is correct, meaning that it falls within the typical observed outcomes, which means there's no difference. All right. So what about errors? Type 1 error happens the most when you reject the true null hypothesis, meaning that you think there is a difference, but there really isn't. Type 1 error is basically what we call a false positive, and does happen, especially if you do not do your statistics properly. Type 2 error is when we fail to reject the null hypothesis when it's completely false. So you say there's no difference when there actually is, all right? That's how you tell the difference. So type 1 is that we reject the null hypothesis and say that there's a difference and there really isn't. And type 2 is when we say there's no difference, but there actually is. So write this down, put this on a piece of paper so that you know what type 1 and type 2 errors are. The probability of a type 1 error when we have the alpha level at 0.05, we lower that cutoff to 0.01, and we reduce the likelihood of committing a type 1 error. So basically, when you're doing statistics and you get something below a 0.05, it needs to be way below 0.05. Otherwise, you have to be careful about your type 1 and type 2 errors, all right? So as alpha gets smaller, B gets larger, which is that probability of a type 2 error. Dealing with these, the only way to really just decrease this concept of having an error is to increase your sample size. So the more you increase your sample size, the higher your n is, or n is equal to sample numbers, and that gives you the power to reject the null hypothesis when it actually is false, because power is 1 minus beta. All right. So it's really important to have a large sample size. Statistical power depends on these few things, which is alpha, which is set by the researcher, set by science in general, our sample size, and our effect size, which we'll talk about. The power you have in your statistics, which is the ability to reject that null hypothesis, is really dependent on these things. Okay, we want to pay attention to type 1 and type 2 error. These 5 or 6 red things on this slide you need to know. You need to know what the alpha level is, the sample size, what an effect size is, what the power concept is, and what type 1 and type 2 errors are. Now we have parametric tests, and this is when we're using normally distributed data. These are always much more positive, or excuse me, powerful. Excuse me. It means that we can really detect even small differences. Non-parametric tests, that's when our data is not normally distributed and it is less powerful. So it can really only detect large differences. So that's why you want to have a large sample size so that you have normally distributed data. Remember how to check whether or not your data is normally distributed. The first thing you do is make a histogram. Sometimes it's really clear, like here on the right and on the left, sometimes it's not. So we do those tests for normality. Shapiro-Wilks is less than 2,000 samples, and the Kolmogorov-Smirnov is over 2,000 samples. You always, always, always do a test for normality. Even if you make a histogram and it looks like this, always test for normality. You have to report it in order to proceed with that parametric test. You cannot go forward without doing that test for normality. If you don't, and you end up with some statistics and someone asks you, was your data normally distributed? And you go, you have to start all over again. But what if you have skewed data and you still have taken like 1,000 samples? You can transform it. I know that sounds a little funky, but it's a mathematical function to shape the data a little bit better so it resembles normal distribution. So say you have data up here, number of fish, excuse me. You take the log of that data and it changes the shape of your data, which allows you to use those parametric tests. We'll talk about that a little bit in a minute. Or you just use a non-parametric test as it's a little bit less powerful, but sometimes you just have to do that. So they don't assume that it fits the normal distribution. So there are equivalents for parametric tests. So instead of a 2-sample t-test, you use a rank sum or Mann-Whitney. Instead of a paired or matched t-test, you use a sign test. And then for the ANOVA, you use that Kruskal-Wallis test. They're not as powerful as parametric tests, but sometimes that's what you have to use. So for now, if your data is not normally distributed, you're going to reject the null hypothesis for either the Shapiro or the Kolmogorov test for normality, and then you have to apply a transformation to make it fit. So what I want you to do is concentrate really on taking that data, and if it is not normal, we're going to work on transformations, transforming your data. So you can do 3 different kinds. There's a few extras, but these are the 3 I want you to concentrate on. There's a log transformation, which takes your skewed data and creates more of a normal data set. This is the code right here, log database. If you need to add 1, say you have like a bunch of zeros in your data, then you have to do data plus 1. Base is replaced with the numerical value of 10. So you would put data plus 1 and then 10. And that's what this log transformation formula is up here. Y equals log of 10 and x plus 1. You can do an arcsign transformation. This is really for things like proportions or percentages. This is the code for that. And then square root is what you use if you're counting a bunch of stuff, like the abundance of something in a sample. And these are the codes for it. That's it for data transformations. Go ahead and answer the questions and then work on the next lecture.